Good morning, everybody. So, first of all, quick announcement. As you can see, we are here for diagnostics and debugging. Anybody who was expecting Lena Smart and conversations around security, you need to go to Richmond Park. Luckily, everyone looks like they're here for the intended talk. So, without further ado, bit of housekeeping first. There will be a QR code at the end of this talk. So these QR codes, you can scan them, and it's the opportunity for you to give feedback on each of our individual speakers. But yeah, as I said, without further ado, I'd like to welcome Arsia Kamsky, our principal engineer from our New York office, to talk about diagnostics and debugging in the cloud.
Hello, hello. Thank you for being awake this early. Well, it's early for me. I don't know about the rest of you, but let's do a quick getting to know each other. How many of you here are developers? Mostly whoa, that is a lot of hands. Excellent. Now, how many of you here have been or are DBAs or were forced to play one because there wasn't an actual DBA? Not as many hands. That's actually good. That means somewhere out there are DBAs that were actually doing that for you. Hopefully it's not that there was nobody playing the role of DBAs. Sometimes that happens. Now, I've done both. I've worked for small companies my whole career, so I've done the developer part, and then I've put on the data architect part and designed the schema back in the old days. Then I'd put on my production DBA hat, and I'd yell at myself like, how could you do it like this? This will never scale, right? Now, I have another question for you, a little survey question. How many of you, when you were little, and you were growing up, were like, when I grow up, I want to be a DBA? Yes, a couple of people raised their hands, yay. Was your mom or dad a DBA? Was that why? Going into the family business? So I was a bit of a strange kid. I did not want to grow up and be an astronaut or a ballerina or a firefighter. When I was little, my favorite thing to do was solving puzzles. And so I knew that when I grew up, I wanted to be a detective, just like my favorite character, Sherlock Holmes. Now, in describing his profession, Sherlock Holmes said that detection is or ought to be an exact science. And I loved science, and I loved math, and I loved all the exact sciences where there were right answers to things. So I was going to be a detective, yay. Now, I'm very happy to be here in London, kind of the home of both Sherlock Holmes and his virtual parent, or his inventor, creator, Sir Arthur Conan Doyle. Now, I don't know if any of you guys know this, folks, but Arthur Conan Doyle was actually a physician before he became a writer. He was a medical doctor, and when he was in med school, he met an incredible surgeon named Dr. Joseph Bell. And Dr. Joseph Bell, he was what we would consider a great diagnostician. He would be able to give you a correct diagnosis based on seemingly a bunch of little unrelated facts. And if that sounds familiar, that's actually how Sherlock Holmes, the character, is, observing just a few bits of details here and there that other people might miss, and jumping to a conclusion that was actually correct, but very stunningly uncanny and seemed obvious now that you mention all of the details that led to it. So Dr. Bell, just like our favorite detector, was a master at a process we call diagnostic thinking. So what is diagnostic thinking? That's really what I want to talk about today. So diagnostic thinking, it's a way of arriving at a true cause of a problem by reasoning about that problem based on your knowledge of the problem domain of the world, combined with observed behavior, what it is that we're seeing, and then application of a diagnostic process to figure out what the right solution is. Hey, pretty pictures. So I'll give you an example of this in kind of in real life. This was, I did not make this up, this was a real life case. So we had a support case. The support case was actually about something else, but during discussion of it, we found out from the customer, from the user, that they were restarting their MongoDB process pretty much every day. And we're like, well, that's really strange. Why is it being restarted every day? And they said, oh, well, it's using up all of the RAM, and the only way we can get it to give back the RAM is by restarting the process. I'm glad to see a number of people in the audience snickering, because probably you're familiar with how Linux works and how processes get the memory they need, and then the rest is used for the file system cache, and this was actually even memory map files, the old storage engine. So basically, it's normal, right? They didn't have the domain expertise to realize that what they're seeing was expected behavior, so they thought there was a problem, right? So both components are important, knowing what the expected behavior is, and then observing something that violates what you would expect to see. So here there was no actual problem. The easiest kind of problem to solve, right? Now, how is the diagnostic process, how does it actually go? Well, Richard Feynman, I don't know if you've heard of him, but he famously said that it's easy to solve every problem in only 3 steps. Step 1, write down the problem. Step 2, think really, really hard. And step 3, write down the solution. Thank you for coming to my TED Talk. No, I'm just kidding, because step 2 kind of needs a lot more detail around it, right? So the actual reasoning about the problem generally consists of 4 steps. We have to get a complete description of the problem and the environment. We have to form hypotheses about the possible cause of the problem, usually multiple hypotheses. We then eliminate hypotheses based on, if they contradict something we already know, right? If they're not feasible given the presence of certain other facts. And then we get to perform experiments to validate the hypotheses that remain to see which one is the true cause. That's the complete process. Here's an example of that process applied to a somewhat trivial, as it turns out, problem. So somebody reported our MongoDB is not running. So what is happening? Well, MongoDB, you expect it to be running. Instead, it's not running. We looked in monitoring, and we found one of the charts that shows free disk space. And we noticed that as the disk space that's free approaches 0, MongoDB no longer runs. And we try to restart it. It no longer runs again. And the hypothesis is pretty straightforward. We probably don't need to gather too many other facts. We say, well, MongoDB is out of disk space. How do we test that hypothesis? Well, we either upsize the disk if it's in the cloud, or we delete some stuff that shouldn't be on there or no longer needs to be on there if it's in on-prem, right? Pretty simple, right? So 4 steps. Now, I would have thought that the generating hypotheses and eliminating them and testing them is the hardest. Turns out the hardest part is actually getting a complete problem description. Complete problem description is super important because, well, if you don't have it, you can go pretty much the wrong way in all those other steps. So to understand the true nature of the problem, you must understand all of the facts around it, right? You have to have a vivid mental model of the problem in order to reason about it. And it's particularly important to gather the complete problem description before you start formulating the hypotheses about what's wrong. It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. Conan Doyle felt strongly enough about this that this quote in different forms appears in several Sherlock Holmes stories, and for a good reason. Right? A lot of times somebody starts describing a problem, and mentally you're like, oh yeah, it's probably this because it sounds like a problem I've heard before. You jump to that, and pretty soon you're going down the wrong track because you fail to gather complete information about the problem. Problem description, the 2 most important things about the problem description are the what and the how, right? What is the thing, the object that has a problem. It's MongoDB or some backup job or some query, right? How that problem is behaving incorrectly sometimes is framed in terms of expected behavior, right? MongoDB is expected to be running, it's down, that's an obvious one, right? It might be that, backup jobs are expected to complete within some period of time, and instead they're running way longer than that. So we get to also other components of the description, like the where, the when, and the size. Where is it happening? It's happening only on the primary. It's happening only in the Asian data center, right? When? It happens after we run a particular batch job, or it only happens on a Tuesday. God, I hate Tuesdays. All problems happen on Tuesdays, right? What about the size of the problem? Right here, it's very important to quantify things as much as possible. Right? Query is slow is not really quantified, right? Backups take longer, but backups used to take 90 minutes and now they take 4 hours, right? That's a quantified size of the problem. Now, problem statements are not just is statements, they're also is and is not statements. Why do we want to draw your attention to the curious incident of the dog in the nighttime? The dog did nothing in the nighttime. That was the curious incident. Right? We can essentially construct a not statement by observing what didn't happen, right? A particular alert didn't go off. Well, probably that means we didn't run out of disk space, right? That sort of thing, right? Things that don't happen can tell you almost as much or sometimes more than things that did happen. Now, I'd already mentioned that exact quantifiable data is far more valuable than subjective data. First-hand evidence is also important in that something that shows you the job started here and it ended there, the query took 93 milliseconds in the logs, is far more reliable than somebody subjectively saying, I feel like the system is getting slower, right? It's hard to quantify. What does getting slower mean, right? So there are a lot of places where you can get this precise data. You gather it, well, from various metrics. So we're talking about the cloud. So you're running Atlas. It's in the cloud. You can get access to the logs, but why? When instead you can go to your dashboard and see a bazillion metrics. I say bazillion because I'm always losing track of all the new metrics that we're adding there. But the cool thing is most of the time when we're diagnosing a problem, we can go there and find some data to show us what is and isn't happening. And now we're going to look at some actual examples and see how we might be able to diagnose those using those metrics. So our first case, this is probably like, I don't know, 70% of the cases. Our queries are slow. Our queries are getting slower. Very high percentage of support cases, people come up to me, they're like, oh, our queries, our operations aren't fast enough. That's very, very common. So we say, okay, when? When did your queries start getting slower? They say around 7:30 in the morning. And we say, okay, where? The primary. This was not a sharded system, so just a replica set. On the primary, the queries started getting slow. And the queries are now taking several seconds where they used to take like less than 100 milliseconds. No good? No good. Something definitely changed. So what we do is we go to these charts and we ask ourselves questions to look at, essentially gathering the data. Are there more queries running now? Because that might cause things to get slower. So the number of queries per second look to be about the same. What about each query? Is it scanning more documents? No, we seem to be scanning, actually it's a lot of documents, but it's pretty steady, right? We wouldn't expect these queries, by the way, these are analytical queries, which kind of explains why the numbers are quite a bit slower than your typical operational queries. I'd expect to take, 1 or 2 milliseconds, not 100. Okay, when we're scanning a lot of documents, is it possible that they're being read from disk? So we check, and first we get excited because there's a spike, but actually it turns out if you look closely at the details of this chart, the The green is actually the writes to disk, and blue are the reads from disk. And they're so small you actually can't really see them. Also, the problem started at 7:30. This write spike of sorts started a full hour before that, so that's probably not related either. That's the detail that shows, right? Read ops at the time that things started getting problematic, 0 per second from disk. So it wasn't that suddenly these documents had to be read in from disk. What about how many we're returning to the application? Are we maybe returning a lot more documents to the application? No, that seems pretty flat also. Okay, maybe we're doing a lot more work. Is there maybe an in-memory sort? So sorts in a query can be either supported by an index, where the documents are read from the index in the order that they need to be returned in, or if there is no such index, then once the documents are gathered, they need to be sorted in memory. Ha-ha! We found the smoking gun. At least we think so. We'd need to then validate this hypothesis, right? But we see that shortly before 7:30, the number of operations that require an in-memory sort went from 0 to 10 per second. Now, if each query is returning a large number of documents and it's having to sort them before it can return them, that's actually quite a lot of work, which means all of a sudden each query is doing more work, which means other queries may be queuing up waiting for that work to be done. I have a talk about that later today around 3 in the afternoon about that sort of thing. So here we go. Oh, sorry. The culprit had been found now. TLDR of the actual root causes, there was some new code that was pushed shortly before 7:30. But if we'd asked the person who reported the problem, is anything in the system changed? They probably would have said, no, nothing's changed, because somebody else pushed the new code. But of course, what changed was the query that was requesting a sort. It's also possible that what changed might have been somebody inadvertently may have replaced one index with a different index. So maybe the sort used to be supported by an index, and now it's not. So keep in mind, you don't always know, when something changes, is there a new query, or is the supporting infrastructure, including the indexes, suddenly different, right? We've had people accidentally drop an index, they thought nothing was using it, and seen the result kind of like this. Here's another case. Oh, shocking. Things are getting slower. Same sort of report, and probably majority of examples that we have to diagnose are kind of like this. So here we go to the charts and look at them all at once, and since there is no specific time indicated, just sort of over time we feel our system is getting slower, we take a look kind of at the whole thing, and as somebody who's looked at these many times now, in the previous example we looked at individual ones, here what jumps out at me personally is that query targeting, right? That is the ratio of the number of index entries or the number of documents that the query had to look at to the number of documents that it returned. Okay, so if your query would give me all the documents where this condition is true, and we have to look either in the index or in the collection at 1,000 documents to return the 3 that match, that's a bad ratio, right? What would be a good ratio? I'm going to call on you now. Somebody yell out the answer. 1, thank you. I was going to say, you guys look so awake. I thought everybody in one voice would yell out 1. 1 is a really good ratio. I don't know, is this big enough for you all to see that the ratio here is somewhere between 3,000 and 4,000? That is what I would call not a good ratio. This means that for every document that we return, we have to look at 3,000 or 4,000 on average, either index entries or documents. That's pretty bad. What does that suggest very strongly? Lack of a good index. I know a bunch of you thought it, because you all look like you're experienced users and debuggers. So how do we see what it is that is causing this? Is this like all the queries are bad, or some of the queries are bad? Am I pressing the wrong button here? Here we go. We go to the Profiler tab. And the Profiler tab will show you slow operations. Now, slow is a threshold that's set by default to 100 milliseconds. But it can be adjusted. It can be adjusted up or down. There's some sampling happens so that you don't see too many data points. And immediately you can see, well, there's definitely some queries that are pretty slow. But in addition to operation execution time, you can also have it plot to you the number of keys examined, the examined returned ratio, which is the thing that we're most interested in here, various other things. And you can look at just for the past hour, 8 hours, 24 hours. So you can click on an operation, and then you get to see the details. And among the details, I think this, yeah, there we go, I blow it up here. You can see a thing called plan summary. That's the query planner. How does it plan to execute this query? What we like to see there is that it's going to do an index scan or something like that. What we don't like to see there is collection scan. Now, collection scan is OK on a really small collection that sits in memory. Maybe it's some metadata, right, that you query all the time. Probably don't need an index. Here we have number of documents examined, 230,000 and change. And the number of documents returned is 1. This is why the ratio looks really bad in aggregate. Now, you might say, gosh, 230,000. I mean, it's not a huge collection at all, right? But that's pretty bad performance. You need indexes, right? Even if the collections are relatively small, right, compared to billions of documents. But of course, what I see when I look at this is, collection probably used to be even smaller, and you used to get away with not having an index, right? Everything fit in RAM, everything was fine. It's the old, I tested it on my laptop and it was fine, but I only had 80 meg of test data. And so I pushed it to production, and in production, things weren't so fine. So things weren't so fine because the collection got too big to fit in memory. And now the other thing we can see here is the number of bytes that were read from disk in order to satisfy this query. And also in microseconds, the time spent waiting for disk, right? So this is, we have to page things into the WireTiger cache from disk or from file system cache. Either way, that's pretty bad. The whole point of indexes is we can very quickly find the one document that we need. And then if it's not in RAM, well, that's only one page that you need to read from disk. So seems pretty obvious that that's the problem. Now, sometimes people go like, well, why did it used to be fast? And you say, well, you know how when you look at these charts, you can zoom out, right? You can look at 24 hours, 1 week, 1 year. And when you look at 1 year and you look at data size and index size, now this was one of their several dozen databases, and you can see that things grew. Every single one of those databases grew. So a year ago, everything fit in RAM, everything was fast. But then as more and more data didn't fit in RAM, things got slower, right? It's the frog being boiled. What's that metaphor they say, right? We don't really notice until our application is dead. Very sad. All right, so trends over time are really important to understand, right? The hypothesis here is that you didn't notice the bad queries and bad indexes when the data was small, but as it grew, the performance got noticeably worse. The way to validate it is pretty simple, right? Create, hopefully first in test environment and then in production, the indexes that would support these queries and watch the performance improve. And how do you know which indexes to create? I mean, there's a bunch of ways, right? We looked at a query. Clearly, we could see from that query it needed an index. There's another tab called Performance Advisor that suggests indexes to create. Now, don't just go clicking create all of them, right? Take a look at them, figure out, find the most impactful ones, the ones that affect the most number of queries. It will also report to you if you have any redundant indexes that you can drop, because indexes are not free, right? For every index, a write needs to update it to maintain it in consistent state with your collection. So you can't just go and add 50 indexes and expect that your writes will stay performant. Cool. So looking at trends over time is kind of important to anticipate problems that happen, right? Both of our examples involved something changing. In one case, new code or a change in indexes caused queries to suddenly become slower. In the other one, it was a gradual process. It's very important to understand what is normal for your system in order to be able to spot things that are not normal, things that may be wrong. And as Sherlock Holmes said, what is out of the common is usually a guide rather than a hindrance. I watched a lot of crime-type shows as well, because they had detective, and I always thought it was really cool how somebody who was an expert in some domain could tell which thing is actual evidence of a crime and what is just kind of a side effect, right? Who was a witness that got splattered by the evidence versus the criminal that caused that splatter to happen? It's a little bit like that in a complex technical system, right? We actually all know that the most scary thing that you can hear a sysadmin or a DBA say is not, oh no, it's, that's interesting, right? Because they're seeing something they didn't expect, and that's an indication that something might be strange or not normal, right? So what is normal? I can't tell you that because it varies from system to system, right? You have to know what's normal for your system. Here's a chart called uplog gigabytes per hour. This reflects the write rate in your system. So for those who don't know, the uplog is a special capped collection, kind of like a circular buffer, where all of the writes on the primary are appended to, and that's how secondaries and change streams and triggers and everything else knows what happens, right? Secondaries tail the uplog and apply those writes to themselves. That's how replication happens. So 150 gigabytes per hour, is that normal? No way to know, right? We're only looking at a few hours worth. So there was some case that came up, and a colleague of mine was looking at this chart, and they zoomed out, and they went, oh, I found something. I found that at 1 o'clock the previous day, something happened, something changed, and that's the cause of this problem that we're now seeing that we didn't used to see. And that colleague of mine would be the first to tell you that what they forgot was to zoom out again. And it turns out that the normal for this particular company was people wake up in this part of the world and start using their application. People go back to sleep, right? They had the type of application that was very regionally heavy used in Europe. And so when the Europeans were asleep, and also during the week, the dips were less. On the weekends, the dips were a lot because it was tied to a weekday. So very important to understand what normal is so that you don't go down the wrong track with diagnosis of a problem. Oh, and of course, the Sherlock Holmes quote, of the highest importance to be able to recognize out of a number of facts which are incidental and which are vital. And that comes to the end of my talk. I love everything about Sherlock Holmes because it demonstrates for us how in a real world we can apply basically the same techniques that doctors, detectives, and DBAs use throughout time, which is we balance the probabilities and choose the most likely. It's the scientific use of imagination. And I would like to thank you for coming to this thing first thing in the morning. And I want to thank Arthur Conan Doyle for creating a compelling character. I'm hoping maybe to visit Baker Street later this week, pay my respects firsthand. And please stick around. We're going to have a keynote in this room in about 20 minutes. We have a lot of great talks. And if you have any questions for me, find me. I'm going to be kind of floating around pretty much all day until my 3 o'clock talk, and then later, and then during happy hour if you stay to the very end. Thank you very much.
Don't forget the QR code, says Dr. Watson over here.
Yeah, if you like
Please
the talk,
scan and
there's
give us
the
your
QR
feedback.
code.